All right, ladies and gentlemen. Today's class recording has started. So, yesterday, we continued looking at our relationship between displacement, velocity, and acceleration, how changes in one affect changes in the other ones. And so the first thing we looked at, well, we talked about the constant velocity and that there was no acceleration and that there was no change, right? The distance it goes, the speed that it's going, everything just stays exactly the same. But then, right at the end of class, we started looking at this ramp where the ramp was tilted in a way that the object was picking up speed at a rate of 4 meters per second for every second. So that's the acceleration of that object along that ramp, all right? And we talked about two equations that we use to relate the different ideas or the different things that we measure about objects as they're going down the ramp. Do I have a separate page of that? I do not, and that's okay. We'll just go right here. Okay? So the first equation we talked about was this equation right here. What can we use that equation to find? Okay. So final velocity, yes, although if we talk about it in terms of what we're measuring, the final velocity sometimes goes by another name, right? What does it go by? The instantaneous velocity, right? We can use that equation highlighted in blue to find the velocity at any time after the object starts rolling down the ramp. Now here, we kept our times pretty even. Not pretty even, we kept them exactly even, 1 second intervals. All that really does is make the math easier to do. We could throw in any time in there. We could throw in 3.7 seconds, or 12.2 seconds, or 14.75 seconds, whatever we wanted, and find out what the instantaneous velocity would be at that moment in time. Okay? Good there? Because the acceleration causes we talked about this being not just accelerated motion, but a constant acceleration. Yes, we talked about that yesterday. Yeah, right? That it's constantly changing, right? What kind of mathematical relationship shows up when we talk about the relationship between velocity and acceleration? I think we talked about this yesterday. What kind of mathematical relationship are we talking about here? Well,
just say anything that's on the board right now. Numbers. Accelerated motion. Linear.
This is a linear relationship, right? Or a direct relationship, okay? It does have a slope, but more importantly for this graph, the slope is constant, right? That's why it's a linear relationship, okay? All right. The other equation that we talked about is that one down in the bottom right. Okay? Obviously, the way that it's set up, we can use that equation to figure out what? The displacement, or how far this object has gone since or while it was accelerating. Okay? If we know the initial velocity and we know the final velocity and we know how long it was accelerating, we can figure out how far it went. And we can look at those intervals. I think we did this here with the guy and his bike. We can look at that interval on a 1 second basis and find out how far the object goes in this particular second here in yellow or this particular second here in green. Or we can look at it over a larger period of time, like 4 seconds or 5 seconds. Okay? Good there? So, last night, I asked you guys if you had the inclination or if you wanted to practice what we were doing in class to figure out how far this or how long this ramp is, right? So first, it gave us an acceleration of 5 meters per second. It's just the next page in your packet. Okay? So it gave us an acceleration of 5 meters per second squared, which, like we said, right, if it's acceleration, it's describing how much the velocity changes, so 5 meters per second for every second. Okay? Up at the top of the ramp, the velocity is 0, right? First thing we're going to have to do is find the instantaneous velocity at the bottom of the ramp. So there's two ways we can do that, right? First, if we just use our definition of acceleration and our logical application of that, right? Each picture of the ball represents 1 second worth of time. If it's not moving at the top of the ramp, 1 second later, how fast will it be moving? 5 meters per second. If this picture represents 1 second worth of time, remember the acceleration is 5 meters per second, it has to go from 0 to 5. And that means the next picture, what would be the instantaneous velocity? 10. Because the velocity has to change by this much every time. Okay? And that means the next one would be 15, and the next one would be 20, and then the next one would be 25. So the instantaneous velocity at the end of the ramp would be 25 meters per second. We could do that in a different way. Remember that this equation here will give us the instantaneous velocity at any point in time, if we know the other things. What was the initial velocity of the ball at the top of the ramp? 0. So that gets plugged in here. We said the ramp was tilted in a way that it gave us an acceleration of what? 5 meters per second, so that goes there. And looking at the picture, how long does it take to get down to the bottom of the ramp? 5 seconds. So either way we do it, either using our logic and definition of acceleration or using the equation, we still get that at the bottom of the ramp, that velocity is 25 meters per second. Okay, good there? But I didn't ask you for the velocity, right? I asked you for how long is this ramp. Right? So, the other equation that I introduced you to yesterday, we can use to figure out how far something goes as it's accelerating, right? So, if we start plugging in numbers we know into this equation, right? What's the initial velocity of the ball in this ramp? 0. We just figured out 2 different ways that the final velocity of the ball in this ramp was what? 25. 2 different ways, but we came up with the same number, and that's good because we should end up with the same number regardless of how we do it. And again, how long does it take the ball to get down to the end of that ramp? 5 seconds. If you do that math right, you end up with 62.5 meters. Okay? Good job, everybody. Well done. All right, how's that? Okay, we will come back to these equations here, probably not today, but more tomorrow when we start analyzing the other set of motion. But first, I want to talk to you about this picture right here, okay? Which you guys have in your packet. It's a little bit small. It's a little bit small up here, so I'm going to zoom it in for you so that we can get a little bit more detail. Okay. So here's a picture of a well, a water well, which I don't know if I've actually ever seen a water well that looks like this, that has a little, like, well, I mean, I suppose I should probably reference SpongeBob more often. to make this real for you guys. So. All right, so somebody takes this rock, holds it over the well, and lets it go. At the very instant that you let the rock go, the fingers leave the rock. What is that rock doing at that moment in time? Accelerating, yes. But is it actually moving? No. So its instantaneous velocity at the instant that we let it go is what? 0. Now, Drew, we said accelerating, right? What does it start doing immediately after you let it go? It starts to fall, and as it's falling, what happens to it? It speeds up in this case, right? Generally speaking, yes, it speeds up. In this case, because it's not moving and it starts moving, it's going to speed up, right? But at the very instant we let it go, it's not moving. Okay? 1 second later, if we could measure its speed, we would see that its speed or its velocity would be 9.8 meters per second. Okay? If we had to make it velocity, we would probably call this velocity what? What does velocity also have to tell us? Well, which way is this rock going? Downward. So we'd probably call it negative. We don't necessarily have to, but most people probably would, right? Although if you called it positive, I couldn't mark that wrong necessarily, as long as you were consistent and called things that were going upward what? Negative, right? As long as they're different, right? So, 1 second after that rock, right, we measure the speed of the rock again, and that speed turns out to be 19.6. Okay? Is the rock accelerating? Yes. Is it getting faster? Yes. Is the distance that it travels in each consecutive second getting longer?
Yes.
Yes. Right? What is the acceleration of this rock? 9.8 meters per second squared, right? This rock is changing velocity by 9.8 meters per second for every 1 second that goes by. The acceleration of this rock is 9.8 meters per second squared. That's an important number, right? First, if the velocity of this rock 2 seconds after we dropped it is 19.6, how fast would it be going 1 second later? 3 seconds after we dropped it? 29.4. 29.4. I didn't know if you guys could read that or not. But so, right? If we go down to the bottom of that well, right, it says 29.4. But how did we get 29.4? Add 9.8 to 19.6, you'll get 29.4. All right? Because it keeps increasing by that much, as long as gravity is acting on it. Okay? So, Matt, go ahead. Really? Interesting. That 9.8 number is important. It is the acceleration that gravity here on Earth causes. Gravity is always affecting the motion of objects. Gravity itself causes a uniform acceleration. A uniform acceleration is just a fancy way of saying what? Constant, right? It is a constant acceleration of 9.8 meters per second squared. It's always happening. However, gravity is not the only, got lost in my words there. Gravity is not always the only thing affecting the motion of an object. If we can isolate gravity and gravity only, we would see that here on Earth, objects would accelerate at this rate. That's important to us because it affects everything we do. So we give it its own symbol, lowercase g. Anytime lowercase g shows up in an equation or a calculation or in a concept, it refers to the acceleration of gravity. Here on Earth, that number is 9.81 meters per second. But we'll see a little bit later that if we go to a different location, the amount that gravity affects things differs based on that location. Okay? Good for starters? All right. Here's a picture that illustrates that concept. First, this picture up at the top confused me for a long time until I finally figured out what it was. So this little part right here is like a trap door that like released and dropped these two objects at the same time. Okay? For the longest time I thought it looked like a printer, and so, but then I was like, oh, that's what this thing is. Okay, a paper towel roll, cool. All right. So here we see another time-lapse photograph of these two objects, right? Just like when we looked at the ball rolling down the hill, or we look at the guy riding his bike. Each picture represents a moment in time. The same moment in time, or sorry, the same amount of time each picture. Okay? It's not 1 second, but it is the same amount of time. What do we see happening to the distance between the apples in each consecutive picture? Keeps getting bigger, right? And we said if we see that, that's indicating what about that apple? It's accelerating. It's speeding up. It's going faster. It's covering more distance each time interval. Okay? What do we see about the feather on the other side? It's also accelerating. Yes? Okay. It's also accelerating as its spacing is getting more and more and more. But, like we said, if we compare it to the apple, right? And it's not the best one there, but it'll go here, right? So there's the bottom of this apple. There's the bottom of that feather. All right. There's the bottom of that apple. There's the bottom of that feather. There's the bottom of that apple. There's the bottom of that feather. What are we seeing about the two of them? They're accelerating at the same rate. They're staying right next to each other. It's probably not something that you've experienced before, right? If you drop an apple and a feather in this room, what's going to happen? The feather's going to go, right? Okay. I think we actually did that in like the first couple days of school, right? Yes, right? Okay.
Yeah,
well, not an apple, but you know. So.
A metal ball that made loud noises.
So, if we can isolate gravity and only gravity, we will see both objects accelerating at the same rate. But when we drop an object in this room, is gravity the only thing acting on it? You got to worry about air resistance. As soon as we throw something else into that mix, like air resistance, or if you're like diving into a pool of water, the water itself, or if we have a big parachute that's catching air, right? Now, gravity isn't the only thing affecting that object, and therefore the acceleration, 1, won't be 9.8, and 2, won't be the same for all objects, because that air resistance affects some objects more than other objects. Good there? So, gravity accelerates all objects at the same rate as long as it's the only thing affecting those objects. So if we want to observe this, we have to do what? we have to get rid of the air resistance, right? So let's take a look at a couple of videos that show that happening, and we'll discuss in just a second. I'm going to stop the recording because the streaming video doesn't show up so hot on the recording, and it makes the recording really, really big. And some of this stuff is copyrighted because it's on YouTube and stuff like that, so I can't like record it and then post it as my own. So lucky we got that on recording. So.